Welcome to Networks Professionals.
Have you ever really stopped to think about what happens when you click a link? I mean, it just feels like magic, right? But behind the scenes, there's this entire invisible language at work, a secret set of rules that makes our whole digital world possible. Today, we're going to pull back that curtain and talk about networking protocols. We'll start with the huge problem they were invented to solve. Seriously, just think about this. You've got billions of different devices out there, made by hundreds of different companies, all running different software, and they're separated by thousands of miles of ocean and land. And yet, they all talk to each other seamlessly. So how? How can your phone in Tokyo ask for a website from a server in Texas and get a perfect answer back in, like, a second? That's the core challenge the internet was built to conquer. And the answer, as you might have guessed, is networking protocols. The best way to think about them is as the internet's universal grammar. They are these super strict, standardized rules that every single device agrees to follow. It doesn't matter if it's your laptop, a smart fridge, or a massive data center in a warehouse. If it wants to get online, it has to speak this shared language.
So here's our game plan for today. We're going to walk through the 4 biggest challenges the internet had to solve. First up, how does any device find any other device? Then, how does it decide between sending data super fast versus making sure it's absolutely perfect? After that, how does all of this happen automatically without us even noticing? And finally, how do we keep all that information safe and sound?
All right, let's kick things off with the most basic thing you need. Before you can send a letter anywhere, you need an address, right? Well, the internet is exactly the same. Every single device that's connected needs its own unique identifier, its own digital address, to solve this fundamental problem of location. And that digital address is all handled by something called the Internet Protocol, or just IP. You can think of IP as the master addressing system for the entire internet. It gives a unique numerical label, that's the IP address, to every device out there. It's basically the zip code for your computer, telling the internet's postal service exactly where to deliver all those little packets of data. Now, this is where it gets really interesting. The original system, which was called IPv4, only had enough room for about 4.3 billion addresses. And, back in the day, that seemed like a lot. But by the 2010s, it was like a giant parking lot that was completely full. There were no spots left. The solution? IPv6. The number of addresses it has is so huge it's hard to even wrap your head around. It's like an infinite parking lot. We are never, ever going to run out of IPv6 addresses. But wait a minute. You and I don't type in long strings of numbers to get to a website, right? We type in names, like google.com. That's where the domain name system, or DNS, comes into play. I love this analogy. DNS is literally the phone book of the internet. Its only job is to look up the human-friendly name you type in and translate it into the computer-friendly IP address it needs to actually find the server. Simple, but absolutely essential.
Okay, so we've got an address. We know where we're going. The next challenge is, how do we actually send the data? But it's not that simple. Do we care more about getting every single piece of that data there perfectly? Or do we care more about getting it there as fast as humanly possible? This is the core problem of transmission. And this slide just lays out the 2 big approaches perfectly. On one side, you've got TCP. Think of it like sending a certified letter. It makes a connection, it numbers every packet, it checks to make sure they all arrive in the right order, and if one is missing, it asks for it to be sent again. It's all about 100% reliability. Then you got the other approach, UDP. This is like sending a postcard. You just slap an address on it and you fire it off. It's way, way faster, but there's no guarantee it'll get there or even what order it'll arrive in.
So the big question is, when do you use which one? Well, it all depends on what you're doing. If you're browsing a website or sending an email, you need every single bit of data to be perfect. You can't have missing words or corrupted file. That is a job for TCP. But if you're on a video call or playing an online game, speed is everything. A single missed pixel or a tiny blip in the audio isn't the end of the world. But lag is the enemy. That's a job for UDP.
So we've covered addresses, and we've covered sending data. But with billions of devices connecting and disconnecting all the time, how does the internet manage all of that without millions of people manually plugging things in and configuring settings? This is the problem of automation and scale.
Let's start with a little automated helper you use every single day, DHCP. Every time you connect your phone or laptop to a Wi-Fi network, this protocol just works its magic. Your device basically shouts out, "Hey, I need an IP address." The network's DHCP server hears it, finds a free address in its list, and just assigns it to you. Boom, you're online. And all of that happens in less than a second. Now, if we zoom way out to the global scale, we find BGP, the Border Gateway Protocol. Look, if the internet is a massive network of highways, then BGP is the global traffic control system. It's what all the huge internet service providers use to constantly tell each other about the best and fastest routes to send data across the world. This is the protocol that puts the global in global internet.
And here's another clever little helper that's probably working in your home right now. Network Address Translation, or NAT. See, your Wi-Fi router gets just one public IP address from your provider. NAT then does this clever trick where it creates a private little network inside your house, allowing your laptop, your phone, your TV, all to share that one single address. It's a brilliant way to save on those old IPv4 addresses, and it even adds a nice little layer of security.
Okay, so we figured out how to find devices, how to send data, and how to automate the whole shebang. But there's one last absolutely critical problem we need to solve. The internet is a public space. So how do we protect our information while it's traveling? How do we create a kind of digital armor around it?
You've definitely seen the solution to this one. For years, the web ran on HTTP. It's the basic protocol, but it sends everything in plain text. Anybody snooping on the network could just read it. That's why today, almost everything uses HTTPS. That little S stands for secure, and it's your visual cue that your connection is private and locked down tight from prying eyes.
So what's actually providing that S with its power? Well, it's another protocol called TLS, which stands for Transport Layer Security. You can think of TLS as the cryptographic engine that's running underneath HTTPS. It's the thing that wraps your entire connection in this secure layer, doing all the heavy lifting to keep your data safe. And this security is really built on three crucial pillars. First, there's encryption. That's what scrambles your data into gibberish so no one can read it. Second is authentication. This is what proves that the website you're visiting is actually who it claims to be, and not some scammer in disguise. And third, you have data integrity, which is a guarantee that the messages you're receiving haven't been secretly changed on their way to you. So to wrap it all up, it's actually pretty simple when you look at it this way. For every major problem the internet faced, a set of really clever protocols was created to solve it. The problem was location, the solution was IP and DNS. The problem was transmission, TCP and UDP. Making it all work at a massive scale, DHCP and BGP. And of course, keeping it all safe, that's HTTPS and TLS. This is the internet's essential toolkit.
And that really just leaves us with one final thought. These protocols were mostly designed for a world of computers. But now, as we're entering this era where literally everything is getting connected, from our cars to our coffee makers, the so-called Internet of Things, what new challenges are going to pop up? What new languages, what new rules will our hyper-connected world need to invent? And that right there is the next chapter in the story of the...
Thanks for watching.